Hello children, welcome back again. In this particular video, we are going to learn the strength of acids and bases regarding Arrhenius theory. Okay. So before that, I want to cut a small thing in the particular previous video. That is nothing but here in the particular given examples of acids. Here I written bicarbonate, right? It is not bicarbonate. It is bisulfate ion. Okay. What is this? Bisulfate ion. Okay, this is a correction for you, and yes, remaining everything is right. Okay, so this is all about, so HSO4 minus is represented as hydrogen sulfate ion or bisulfate ion. Why the word bi came in? Because of the presence of H. If you see anywhere H, single H in the particular chemical formula, we can represent that as bi. Okay, SO4 minus is sulfate bi with the combination of H. Okay, here we go with the topic starts of strengths of acids and bases. Okay, strengths of acids and bases, and this particular topic is already revised in the classification of bases, the first classification, that is based on, yes, the classification basis on the basis of strength. There we discussed regarding strong bases and weak bases, right? So that theory is again included in the particular Arrhenius theory. Okay, accordingly with the particular, the liberation of OH minus hydroxyl ions, and based upon the degree of dissociation, and also based upon the high concentrations and low concentration, everything is done, no? Yes, in that particular classification of bases we discussed all that regarding strengths of bases, and here based upon the Arrhenius theory and what it is telling about the strengths of acids and bases, let's see over here. Okay, ready? Here we go with the theory according to Arrhenius with the strengths of acids and bases. Okay, here strengths of acids bases according to this theory. Which theory? According to whom? According to Arrhenius theory. Very good. Acids which dissociate to a large extent, okay, and produce in aqueous solution large number of H plus ions. Children, we know that acids do liberate H plus ions in aqueous solution, but the topic here is the acid which are liberating more to large extent, dissolving and are producing large number of H plus ions are called as which acids? Strong acids. Yes, absolutely true. Yes, and those which dissociate to a smaller extent, less in number, okay, smaller extent, and produce less number of H plus ions are weak acids. So what are producing? See, for example, large extent, large number of H plus ions, those are called as strong acids, and small extent and producing less number of H plus ions are called as weak acids. We know this already, right? Do you remember the topic over there? Very good. So those are liberating high concentration, which means large number of H plus ions about large extent is called as strong acids, and those are giving small extent of less number of H plus ions are known as weak acids. What is H plus? Which ion is that? Very good. H plus means it is hydrogen ion. Okay, very good. Now, examples of strong acids and weak acids. We know this already regarding the acids topic. Yes. Okay. Here, HCl. Example here. Here we go. Example: HCl, H2SO4, and HNO3, etc. are strong acids, and CH3COOH, H3BO3, HCN, etc. are weak acids. Okay. Now tell me the names of all the things of given chemical formulas. Tell me, what do you understand regarding all these things? HCl is named as which acid? Come on, tell me. HCl is named as, tell me. Hydrogen chloride or hydrochloric. Come on, tell me. Hydrochloric acid. Hydrogen chloride or hydrochloric acid. Very good. Now, next one, H2SO4. H2SO4 is named as what? Sulfuric acid or hydrogen sulfate. Okay, and HNO3, nitric acid or hydrogen nitrate. So these three and so many other etc. are regarded as strong acids, and namely these three and etc. also are called as weak acids. But what the three we given, let's learn it. Okay, CH3COOH is represented. No, this particular acid name is known as acetic acid. What is that? Acetic acid. Okay, and H3BO3, this acid is represented, no, second in the example of weak acid. What is its name, children? H3BO3. It is named as boric acid. What is this? Boric acid, yes. Okay, now third example, HCN. What is HCN? HCN is named as hydrogen cyanide. Hydrogen cyanide. Okay, so these three include the names. CH3COOH is named as acetic acid, H3BO3 is named as boric acid, and HCN is called hydrogen cyanide. These are the examples of weak acids. Okay, whereas HCl, H2SO4, HNO3 are strong acids. Okay, so you already wrote the names in the previous slide, previous video, H2SO4, HNO3. So hence there is no place in here. Okay, fine, no? You know the names? Very good. So these three are new for you, so written the names over here. Okay, fine, very good. So this is all about the acid, the strength of acid. Based upon that, we are differentiating based upon the large number and large extent of production of H plus ions. We name it as strong acids. And what about weak? Small extent producing less number of H plus ions, we name it as weak acids. Okay, this is all about the examples of the strength of strong acids and weak acids. Now next is, guess what? Yeah, bases. Yes, so similarly bases are also given the definition like that only, but in the place of acids we write bases. In the place of H plus ions we write it here as OH minus ions. Remaining all are same. Okay, the definition is like this. Similarly, bases which dissociate to a large extent in aqueous solution produce a large number of OH minus ions. Are which bases? Definitely those are strong bases. And what is opposite to that? Large. Yes, large extent means small extent. Very good. And those which dissociate slightly, giving a few OH minus ions. See, remember the word few. Few means takwa, chal takwa. Okay. Yes, less number. OH minus ions in aqueous solution are called weak bases. So those bases which give large number of OH minus ions are named as strong bases, and those bases which liberate few, which means less OH minus ions, are called as weak bases. And here goes the examples for you. Yes, NaOH. What is NaOH? Sodium. Sodium. OH means hydroxide. Very good. Sodium hydroxide or sodium hydroxide. We have examples. We'll get okay. Sodium hydroxide NaOH and KOH potassium hydroxide and BaOH twice. What is BaOH twice? Here we go. Right here. BaOH twice is named as barium hydroxide. Barium hydroxide. Okay, so this three, NaOH, KOH, BaOH twice, called as barium hydroxide etc., are called as the examples of strong bases. Okay, and while NH4OH, CaOH twice and AlOH thrice are examples for weak bases. Okay, NH4OH means ammonium hydroxide, yes, and AlOH thrice means aluminium hydroxide, and here children I want to do a small correction regarding this. Here given calcium hydroxide is there, no? This is regarded as strong base, okay, but not as weak base. You know why? Because strong base which do contain See, CaOH twice is having some exception, that is CaOH twice is a strong base, is a strong base. You know why? Because it gives rise to CaOH twice, it produces high concentration of OH minus ions. Because of that we mention CaOH twice, calcium hydroxide, as a strong base, but it is having one disadvantage, that is calcium hydroxide is sparingly soluble, which means తక్కువ కరుగుతుంది అన్నమాట, చాలా rare. Okay, slightly, we can use the word slightly or sparingly soluble. Okay, sparingly soluble, or you can also write slightly soluble. Because of that reason we mention calcium hydroxide sometimes as a weak, but because of it producing OH minus ions to a larger extent, we have to represent calcium hydroxide as a strong base but not at all a weak base. Okay, because of that I am writing here calcium hydroxide as as a particular, one second, here I will represent calcium hydroxide as a strong base but not at all a weak base. Okay, so here let us write, I will write mention here also. Okay, including with particular, one second, I will write here in top also. Okay, I will cross this here and I will mention this in the previous strong bases section. Because why? Calcium hydroxide sometimes it is, not sometimes, all the times it is regarded as strong base because of the reason why it is producing more OH minus ions in aqueous solution and it is sparingly soluble. If it is soluble or else no, it is secondary issue, but it is giving rise to more amount of large number of OH minus ions, right? We have to include in that a strong base. That's the reason I am including the strong base. Okay, so if there is any doubt regarding this, you have to mention and clarify regarding the particular OH minus ions. Calcium hydroxide, upon dissolving in aqueous solution, it gives rise to large number of producing more OH minus ions. For that reason we mention calcium hydroxide as a strong base but not at all a weak base. Okay, here it is small correction for you. Okay, yes, and here given ammonium hydroxide and aluminium hydroxide, NH4OH, ammonium hydroxide, AlOH thrice, aluminium hydroxide, these two and some other examples are also there for regarding weak bases. Okay, but here the main important point, the exception here for calcium hydroxide, make chart corrected, okay, in your books. So here it is all about the similarities of acids and bases regarding the strengths and according to Arrhenius theory. Okay, now we will see what's next. Yes, the acid base strength can be quantitatively compared through their dissociation constants. Children, we know the strength is only based upon the dissociation, the degree of dissociation alpha. Do you remember that? The classification concept of acids and bases. So in that the dissociation is very important because why? It dissociates only and it will give liberation of H plus ions and OH minus ions. Okay, upon this acid or base, upon dissociation, aqueous solution gives rise to H plus and OH minus. Yes, so in that particular dissociation constants we will represent it as K. Okay, that dissociation constant represented as K. Okay, once again, the acid base strength can be quantitatively compared through their dissociation constant. For the acid HX, the dissociation constant is K is equals to H plus X minus by HX. Children, quantitatively the word which means it is giving a number. Quantitative means it is telling about the number. Quantity, we say no. Quantity means the number, total number. Okay, we know degree of dissociation is equals to number of dissociated molecules by total number of molecules, yes, into 100, we don't know. So all this is all about that, but here dissociation constant regarding acid is given as K is equals to, because K is dissociation constant, K is equals to H plus, which means it is a hydrogen ion, and X minus means it is a negative radical or anion by the complete acid formula HX, because H's were taken, so HX. Okay. And similarly with that of base, what it is there? MOH, no? See, the constant, this constant is usually written as, what is this? Ka means, it is constant for acid. Okay. Ka means constant for acid, remember that. Ka means constant for acid. Ka means dissociation constant, and A means constant for acid. It is written like this, Ka. Okay. Ionization constant. This constant is usually written as Ka, which means it is a ionization constant. Okay. So here, of the particular acid, A means small a, no? A means acid. Okay. Now, similarly for base such as MOH, actually up to here is a particular one for this acid, and from here it is different. Similarly for base, which means MOH, the representation is K is equals to M plus, which means it is a cation or positive radical into OH minus by formula MOH. That is the given constant for dissociation constant for base. Here what is for base? For base we written as K, capital K and small b. Okay, for base. K means for acid, Kb is for base. Kb is for base, because why? The B letter is included. Here why? A means for acid, K means acid, because why? A means, you don't know. This is all about the formula, how to do it. See, it is remembered as quantitatively compared, which means numbering is compared. Large number, small number, no, through that we are comparing. Okay. What's next we'll see? Okay. This constant is usually written as Kb ionization constant for the base. The before section we know, no? Here Ka means for, K is the ionization constant for acid, Kb is for ionization constant for the base. Okay. Now, the larger the value of K or Kb, the stronger is the acid or base. Okay. So, the larger the value of K or Kb, the stronger is the, actually here the word A is missing, just a second. A, okay. Yeah. So, if there is larger value of Ka or Kb, that means it is giving about the strength, which means why, children? I told you know here, quantitatively means giving the number, representing its number. If the K and Kb values are more, then what is the reason? It is dissociating more number of H plus ions or else OH minus ions, which means it is a strong acid or a strong base. That's the reason. Okay. The larger the value of Ka or Kb, the stronger is the acid or base, because why? It is dissociating completely. More number of ions are being produced, so it is definitely a strong based upon the strength. Okay. For weak acids and bases, Ka and Kb values are small. Remember, very important. Okay. For strong acids or strong bases, the Ka and Kb values are more, large. Okay, large. And for weak acids or weak bases, the Ka and Kb values are small respectively. Okay. And however, for acids such as HCl, H2SO4 and HNO3, what is 3? These three are strong acids, no? Hydrochloric acid, sulfuric acid and nitric acid. For these three, Ka, what is Ka? The dissociation constant for, the ionization constant for acid cannot be determined. See, there is an important word over here, children, note it down. There is an exception here, from here to here. Exception, point to be noted, okay. The Ka value cannot be determined for the three acids. What are three? HCl, HNO3 and H2SO4. What are the three namely? HCl means hydrochloric acid, H2SO4 means sulfuric acid, HNO3 means nitric acid. For these three, Ka value is not determined, not given, can be determined. Why? Because these acids undergo complete dissociation. They undergo what dissociation, children? Complete dissociation at ordinary dilutions. Because why they are highly producing H plus ions, no? So they will completely dissociate in the dilute solutions, ordinary dilutions, okay. And equilibrium does not exist. Because of that, if they completely dissociate in ordinary dilutions, in the sense ordinary, okay, in that condition, how can we calculate the Ka value? Because it is completely 100% dissociation is going on, no? So in that case, there is a difficulty to find out the Ka, means what? The dissociation constant of an acid. Because why? They are completely dissociating into H plus ions. So that's the reason the equilibrium does not exist. So we can't calculate the given thing. So the values cannot be determined. They're asking us, they're telling us, okay. And same is the case for the strong bases such as NaOH and KOH. For this also, the Kb value is not determined properly. Because why? They both also completely dissociates and the equilibrium does not exist because of complete dissociation in the ordinary dilutions. This is about the reason for the particular only strong, such as strong gases, strong bases regarding this. Only these 5 exceptions, okay, namely HCl, H2SO4, H2O3 for acids, and NaOH and KOH for bases sections, okay. So these 5 are some important the marked note point regarding the particular strengths of acid bases, okay. This is all about the strengths of acid base according to Arrhenius theory, children. Hope you enjoyed the class and regarded all the things of exception, you noted down all the things, okay. The star marks is all about the concept, and watch the video continuation in the next particular video, okay. Thank you.